Thank you all for being here. I know it's Friday, I know it's late. We've all assumed a lot of information, met a lot of new people. Now we're getting pretty tired here, but thank you for coming. We'll keep this pretty short and sweet, a little bit more discussion based. So in the interest of time, we'll go through the slides a little bit more quickly and then leave it open for Q&A or to make it in time for the lightning talks. And so what we're going to talk to you about today is interpretable anomaly detection for numerical data in Python using a little library called PyNomaly. So first, hello, my name is Constantinou. I'm a data scientist. I've also been a machine and deep learning engineer, software engineer, and I also like to create things, right? If I have to sum myself up, I've worn a lot of different hats. I like shifting roles, and I really just like creating things that people love, building tools especially. So my current gig is at a company called InFactory. If you want to check us out, InFactory is a fact-based platform that enables developer teams to easily leverage complex data sets in their AI products for more trustworthy AI. So if that sounds intriguing to you, do check us out at infactory.ai and join our waitlist.
Hey, so I'm Tiras. I'm a senior software developer from Germany, and my main area of focus is observability and the mixture of that with machine learning and ML ops, which is also how I got to become a contributor to the container of PyNomaly, because it was already a bit in my area, and so I can talk a little bit about that later.
Perfect. So what we're going to do today is we're going to talk about what the library is, specifically what it is and what it isn't, why you should could consider using it, and then in that section we're also going to talk about situations where this particular algorithm would not apply, so a couple of gotchas. We'll go through a little demo, and when I say demo, we're just going to go through the README. It's got some great examples. I don't want to introduce unnecessary risk by firing up the terminal window right now. Then we'll look at the outlook, what's our pathway to 1.0, a couple of things that we're considering, and then just some Q&A. So what is PyNomaly? It's a Python 3 implementation of an algorithm called local outlier probabilities, or LOOP. And that algorithm is a local density-based outlier detection method. It provides outlier scores in the range of 0 and 1, and those are directly interpretable as the probability of that particular sample or that particular observation being an outlier. And that's pretty convenient. Not a lot of anomaly detection algorithms spit out a normalized score. Sometimes that's something you have to do after the fact, and it's not necessarily clear where to draw the line, which Ekin will talk about here in just a little bit. So PyNomaly is Python, I presume that's why you're here. We're at PyData, right? But it's a pretty lean implementation. It's Python and NumPy. It's platform independent. I've used this software on x86 machines, on ARM machines. I've even used it on a IBM Power 8 machine, a computing cluster at my previous job. So it can pretty much run everywhere. It's really only enough you need. The batteries are actually not included. So, part of the selling point with this library is that it's very lightweight. It only implements this algorithm in one derivation of it. If you're looking for a lot of other things, go download a library, use a library that, has, what you need. But it can be used on data frames, e.g. pandas, and I guess one of the big things is that it's under an Apache 2.0 license. It's open source, so very permissive. Feel free to use it both in your commercial and open source settings. So like I mentioned, it's an implementation of local outlier probabilities, or LOOP, which was introduced in 2009. So this is not like a new breaking, great way of doing anomaly detection, but it's good, it's reliable. And there's a streaming implementation approach that came out in 2016, which our library also implements, which you see here. And so as new data points are coming in, they're getting scored against a previously available set of data that you might have fit on previously. And so that's kind of what's happening here on the animation on the right-hand side. And so we brought this about in 2017. We'll go into that a little bit more, and there's lots of good reasons to use this approach, which Ekin will talk about. Lastly, it's stable. So, we introduced it in 2017. It's been around. It's not necessarily had a lot of changes because, again, it's a couple hundred lines, and it's this one particular algorithm. But it was peer-reviewed in the Journal of Open Source Software, so if you haven't heard about that this week, do check it out, do check them out. It's a great way to get some of your software peer-reviewed. I've done some reviews for the Journal of Open Source Software. It's not something I do actively now, but it's a good way to get involved. And our library is a core library of deep checks and PySAD, which is Python streaming anomaly detection. So do check those two libraries out as well. So this is kind of a funny slide because if you understand NetworkX's download stats, it's like 80 million, right, in the last month, right? So this just kind of puts it into context of just how small and lightweight this library is. It really meets a particular need. And this is kind of what our download statistics look like. I mean, if you actually look this up today, it's about 54,000 in the last month, which is which is pretty good. These stats are available on our website and in our README. If you're developing your own Python open source software, one thing that you could do is actually link this. If you've got your software PyPI. So a little bit of PyNomaly through the years, and I want to talk about this just to encourage folks here to build their own software, even if they don't necessarily think there's a core audience, right? Because I built this for myself. Starting out. We were exploring different types of anomaly detection approaches at an earlier job, which I'll tell you about here in just a minute. And this implementation existed in R, but it didn't exist in Python. So the first version was extremely naive. It was like double, triple for loops. It was super slow, but it got the right results, and that's what it mattered. But I continued working on it. In 2018, we added a streaming implementation, which I talked about after kind of doing a year of stability fixes. In 2019, we added Numba support. It's optional, but if you do install Numba in your environment and set a particular environmental flag, the core distance metrics operation will be just-in-time compiled. So it'll be a little bit faster than if you were doing it purely on CPU each time. And all of this happened when I was at my job at the NASA Jet Propulsion Laboratory. So if you're unfamiliar with that lab, it's a federally funded research and development center. It's the only NASA lab that's not run by NASA. It's run by the California Institute of Technology, or Caltech, and so there's a big emphasis on open source work. And so that brings us to now. You can see there's been not a lot of version changes. It's been pretty stable. We've just had some minor bug fixes that we've done over the years. And so Ekin's going to talk to you about why to use this approach and when it's convenient, and then I'll talk a little bit about when that doesn't hold.
Yeah. So why should you use PyNomaly? Basically, we need to take a step back there and look at anomaly detection in general. So what even is an anomaly? It's really dependent on the topic you're talking on, like on the area. An anomaly in market data is something else. If you are working with sensors and machine data on something, it's another thing. And so you really have to have a certain degree of domain knowledge to even evaluate what an anomaly is. So this also means that there are lots of different models and they all suit a particular need. And there are, for example, global models that look at the entire data set and determine whether something is an anomaly with regards to the entirety of the set. And there are like local models that look at the local cluster and decide whether it is a local anomaly. An example for that would be a spike in a time series. It can be that the spike is completely normal for the overall time series, but it is an anomaly on Sundays. That would be like a good example for the difference. So another thing that you should always consider when you do anomaly detection is that it usually triggers some kind of action, whether it could be an automated action or it could even be a human operator. So what that means is that oftentimes false positives can be more harmful for a detector than false negatives, because this will lead to your operators to start ignoring any alerts. So it will become basically, they will stop using it at all. And another issue that arises with anomaly detection is sometimes you do not know the underlying data distributions, and certain models require a certain set of distributions that they are only applicable on, or the stuff might even change over time. Like if you have, for example, a certain behavior in your machine while you are starting up with your company or something like this. If we're talking about observability data, for example, the patterns in there might be different than when you're fully used or you found your market fit and it's suddenly people who only work on Sundays with your software or something like this. The stuff can change. So what you need to know with the interpretability of anomaly detection, which is our topic, what we mean by that is actually how you interpret the scores. So because there are lots of different models, some of them produce labels where you do not know, okay, this is an anomaly or not, but you have difficulties assessing why it is considered an anomaly, like how high was the underlying score, and in what relation does the score stand in. I will give you an example about LOP in general. So LOP is a density-based method. It assigns an outlier score or a probability of an object being an outlier based on its local neighborhood density. So what does that mean? There are similar models to it that you might have heard of. It's like local outlier factor, for example, is a commonly used model, which will provide you with almost arbitrary score, for example, as I will show in the next slide. While LOP, since it does use a probabilistic distance, so it creates a context set, which is the neighborhood of it, and then does like compare the score that you actually get, the density of it, to the expected density, and normalizes that and gives you a nice clean score of 0 to 1. And I will show you why that is important in the next slide, which you can see on here. So here I compare the scoring between an LOF model and an LOP model, where you can always see like the LOF score, for example, which is what we mean by interpretability. Here on the lower side, you can see that it has a score of 4 suddenly in a cluster. And up there, the score basically doesn't have an upper bound. It has a lower bound, which is 1, which means it's a normal data point, but the upper score does not exist. So if you want to try to create a threshold for your alerting, and you want to pick it in a way that it is meaningful for you, it's really difficult because the range is different, even in the same data set between different clusters, and it is also different between other data sets. So it's really, you have to have a more complicated way of calculating your threshold where you want it to be. And as I said, you want to avoid false positives, so you might want to set it a little bit higher. But what does that mean in this context? It's difficult. It's not impossible, but it is difficult to assert, especially if you're working with lots of different time series like we do in the observability area. So a score like LOP, which is always normalized between 0 and 1, gives you probability and gives you comparable scores as well. Like you can compare the score in one cluster within the data set with another cluster, and you can also compare the scores across the different data sets. And
yeah. Great description, by the way. All right, so Anomaly is really easy to use. So that's another thing. What you see in this code snippet here on the right-hand side, that's the minimum amount of code you need to get started. So it's compatible with pandas and NumPy, as we mentioned. We'll get into this a little bit with the demo, but it's possible to use scikit-learn's KD tree implementation and bring your own distance matrix as well. And like we mentioned earlier, there's Numba support for parallelization and just-in-time compiling too. Did mention this earlier too, but we do support the incremental loop algorithm. So this was an algorithm adaptation introduced in 2016 that also allows you to use this approach on incoming streaming data, provided that you refit periodically to make sure that your underlying data distribution still meets your assumptions. But loop fails, in certain situations. And so, I mentioned that, I originally built this, for me and my team. We were exploring different algorithms to use at the NASA Jet Propulsion Laboratory. So the context was we were trying to build real-time detection systems for space capture telemetry, that's coming in off the vehicles. And we needed, some robust means to do that. We did not end up going with local operability for what you're about to see, actually. But there's a couple instances where it fails. One where the anomalies are actually well within the normal density of the data or the distribution. So I'll show you that in a minute. Or when the anomalies are considered an aggregate. So loop actually scores each individual observation, right? It has no thought of time or context. And so we'll kind of talk about that here. And so let's say you work for a healthcare company or an engineering company, and you might be using oscilloscopes or something that generates sine wave-like data like this. So this is a fixed frequency, it's a fixed amplitude. We expect to kind of see some repeated behavior. I'm going to introduce two anomalies here. So I perturb the data just a little bit here, and force the signal to jump a little bit at the top and jump a little bit down at the bottom, change the magnitude. This, is an anomaly. I mean, if I was doing this in my spacecraft context, this is something I'd want to flag. Similarly, if a value is flatlined in the middle of what should be a sine wave, right? This is clearly anomalous to me. This is clearly anomalous to you, probably to most people that would be looking at this. But if I were to apply, this particular algorithm to this set of data, it's going to think that this is normal because this is well within the normal density of the data. And so I'm going to show you that right now. The red points are what this algorithm believes are anomalous, and the blue points, or the darker blue, are more normal. And what you'll see is that what's flagged as anomalous is just where there's little density, right? So this is just going to show that you really need to know which algorithm still to apply in which context and know what the goal is for your problem. Even if this kind of algorithm provides a very interpretable way of understanding, the result set. And so I did want to highlight this out. It's not, anomalies are very complicated. They're very context dependent, as Ekin mentioned. And so I did want to point out too where this will fail. And so I call this demo, but we'll go through the README here just real quick. And so we have a lot of examples on the README and a lot of descriptions. So I've been building this up over time. I think you can come here and get all the information you need, but just a couple of highlights. We do support Python 3.6 all the way to 3.13. Yes, we still support 3.6. We had to do a little bit of tweaking in our GitHub testing workflows, in order to get that to work. But like I mentioned, and here I'll make this a little bit bigger. Getting started is very easy. From PyNomaly import loop, you're going to define this local outlier probability class. You're going to pass your data, and you're going to fit. You're going to extract your scores, and you can print your scores if you want. If I wanted to change some of the parameters, so we're not going to get into exactly what the parameters, list extent parameter means. We can refer you to the paper just in the interest of time. But there are parameters in here that you can perturb in order to get some different results. Very similarly, you all are probably all familiar with the Iris data set, or at least most of you. We've got some 2 well-formed clusters, in the Iris data set. I believe it was based off of the petal length and the petal width, right? And so you might imagine a situation where I actually want to, separate my clusters first, consider them completely independently, and then apply this algorithm to each. And so I could use the dbScan or any other clustering algorithm, get some cluster labels, and you can actually pass those, along as part of your fit, as part of your definition, and then the algorithm will apply separately, on each one. And last but not least, just in terms of the demo, then I want to get back to, the slides and open up for questions, is that I mentioned earlier that you can bring your own distance matrix. So the definition as it is in the paper is based purely off the Euclidean distance. Now, recognizing some modularity in our code, you can also actually bring, and this is an extension of the paper, it's not in the original definition, but if you wanted to provide your own distance matrix with your own distance metric to define what those distances are, you can do that. So let's say I was importing, from sklearn, I was using nearest neighbors, and I wanted to define a different way, a different metric for my distance. Maybe it's the Hamming distance. So I can do that. I can retrieve my distance matrix, and I can take that straight back along with my neighbor matrix, which gets spits out at that operation, and I can get back my scores. And what that looks like, and I'm going to actually zoom back out so we can get the whole thing on the screen here. So these are distance metrics for the same Iris data with different distance metrics, right? And so you can see how the Euclidean distance is, right there in the middle, far on the right. But this provides you, the user, some flexibility based off of what you are working on to provide your own distance matrix as well. And so I'll leave it at that with the README. There's lots more in the README, but we are available on the Python package index as well as Conda. So whatever you're working with or whatever tool you're using, you can go install. All right, so Outlook, and then we get some questions. So we have some proposed API changes. They're, the existing API is pretty intuitive, but it could be slightly cleaner. And what I mean by that is, right now we pass the data along when we instantiate this class, and I think it'd be a little bit cleaner to just define the parameters here, for how loop is actually executed, and then you pass your data instead as part of the fit call. So this is something that we envision kind of doing in the future, just kind of as a heads up and making the API a little bit more clean. One thing that I personally find very exciting, and I'm sure a lot of you do know with these, with the generative AI and what it's doing, is you can use them as peer programmers, right? I think Google in their third quarter results recently said, I think 25% of our new code is AI generated, and it's really kind of accelerated their workflows. Well, that's no different for open source. So, and I'll give you an example. Issue number 49. There was an issue with the cluster labels where the essentially it was an indexing issue, right? This is something that a user brought to us. It's not something that I noticed. It's not something that I can notice. But being in this area, I created a really nice prompt. Given that it's open source, I actually minified the code base and I provided that as well. And it spit out a result. I said, okay, so I took that and I wrote my own unit test. Passed, which is great. Up to 10 decimal points, same answer, so it fixed the issue, right? And then we had Econ review, right? And the process was very quick, it was very easy, and it allowed us to save time, and really focus on making sure that the implementation and the fix was correct. And so, I personally find that exciting, and I hope you guys do too. Last but not least, if you find this algorithm useful and you typically are in a workflow where you use scikit-learn and other parts of scikit-learn, then click on this PR and give it a thumbs up. Because this is probably the third or fourth PR over the years, over the last 6 years, where this algorithm has been introduced by somebody in the community for inclusion in scikit-learn. It's probably the third time I've reviewed those changes, and it kind of stalls after that. And so, I don't necessarily have a huge vested interest in getting it in there, but if it's something that you all, believe you could use, please go in there, click on this link, and give it a thumbs up or say, hey, I would use this. Yeah. Sorry, did you get your picture?
Yes.
Yeah. Okay, great. All right. So with that, we'll open it up to questions and answers. I did want to keep it brief. It's the end of the day, and we do want to get to the lightning talks too. And importantly, I kind of want to hear, where you guys all do anomaly detection too. And thank you. So, this is how to get in touch with me. This is how to get in touch with Econ. Like I mentioned, I'm in California. I'm in Pasadena right now, and Econ's based out of Germany. And so, fun little open source story, when I was developing software a long time ago, and the way that Econ and I got in touch was I put up a call, on the README for maintainers. I was just said, hey, I need help, And I don't know, probably 6 months or close to a year went by, and I get an email in my inbox. And it says, hey, Econ, I tried to use your software at work. I'd love to help you maintain. And so that was a pretty cool story, right? So it's cool to have that community. Now we're here, in person together. And so, thank you for letting us be a part of this and sharing our work. Let's go to the back first. Yeah.
I was struck by that sinusoidal example.
Yeah.
What about other things like taking windows and considering that as like a vector anomaly detection or something?
Yeah, that might be possible.
Yeah.
I have done windowing approaches before
Yeah.
In the past, for other types of applications for anomaly detection. But yeah, that might give you what you want, because then it might be slightly out of distribution within that window. But then you're playing with window sizes and some other things too.
You said like that's a sort of great example of what you do with JPL,
Mm-hmm.
and you also like built and used this at JPL. Like,
Mm-hmm.
was there some kind of, if you're doing like anomaly detection sensor data at JPL, for example, what did you use? How do you attack this?
Oh, so how did we attack this? Okay, so I will say if I went back and did it today, I'd actually do something different than what we did at JPL, but I can kind of give you a little highlight. So we ended up finding that the patterns that we were typically using for were, highly nonlinear patterns, but were correlated across channels because the vehicle is doing something, right? Or it's being impacted by the environment. So you're going to see anomalies not just in isolation on one channel, very typically, but more often than not, in the vast majority of cases, across several channels, right? And typically by subsystem, in some related system. Unless it's an environmental factor, in which case it'll show up everywhere. It might show up in your battery data and your solar panel data, right? All kinds of stuff. Even your heat sensors, because it might get cold. And in that case, we ended up using, I guess this was 2018 at the time. We used an LSTM. And so we used a windowing approach, and we predicted going forward what the value would be. We had some residual, and then we came up with an automatic way of drawing whatever threshold that should be, for those residuals. That presented some complications in that you had to assume continuous data because we're using LSTMs. There's some lag between when the LSTM is able to respond to the new information and detect an anomaly. And so there's always this kind of blip in the residuals that was kind of hard to deal with. What I've done in subsequent work, same sort of context, time series anomaly detection, but not spacecraft data, another type of time series data, was again use a deep learning approach, but use an approach called gray mean angular difference fields, or GADF, to convert a window of time series into a picture, actually. And that dramatically simplified the modeling pipeline because all of a sudden it's just it's random sampling for your picking up your training and testing data. It's just a binary classification problem, and that was really convenient. So the way that would work is new data comes in. You have some window of data that gets converted to an image, and then that image gets put into a computer vision model, and an outcomes result. And there are some challenges there in terms of performance, but it was more than worth it for how dramatically simplified the pipeline became. Hopefully that answers your question.
Yeah, I'm gonna find you after.
Okay, cool. Yeah, all right. Up here.
I was curious whether this algorithm could extend to higher dimension data. So for example, the ones that you showed were for every value of X, the target was Y, but if you had, let's say, some kind of heat map where
Mhm.
you have X, Y, but the target is Z, so
Yeah.
would this extend to
You
something?
can
Yes.
use it on multivariate data.
Multivariate data, you have the same problems with any distance matrix. The bigger your matrix, the sparser it is, right? Distances become less meaningful, right? Same problems, but yes, you can apply it to all kinds of multivariate data.
Thank you.
Yep. Mhm.
I ran a quick example while you were talking where I generated a range from 0 to 1,000. And then I
Nice.
just-
Did you open a fix or a
Yeah, and I said 1 point to 500,000, 1 point to a million. And sorry, 1 to 5, yeah, I think that's what it was. And the 500,000 one was considered the anomaly, and the million one was actually very close to 0, and I didn't understand why.
That's interesting. So it's 3 points or 2 points.
No, I did 1,000 points.
Oh, you did 1,000 points.
Yeah, so
Okay.
0, so 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 1,000.
Mhm.
And I just randomly overwrote a couple values to be 500,000, 1 million.
Mhm.
And the 1 million was not considered an anomaly. I don't
Interesting.
understand why.
Okay.
So maybe it makes sense to play with the distance function.
Distance
You
function,
use
yeah.
it.
I was saying intuitively, like, I guess, pretty confused. That's why I
Yeah.
wrote it. I thought you guys had.
Sometimes you get that, yeah.
Yeah. Yeah. Any questions? Any other questions, thoughts?
Here.
Okay. Yeah.
What's next, and what do you want to build?
That's a great question. What's next? I mean, well, this is pretty stable. I mean, I don't plan on doing much with it other than that, like, API change, right? It gets downloaded a lot each month because it's part of the deep checks library. They obviously use it in some way. I actually haven't checked exactly how they use it, but it's used, fairly regularly. I mean, what I kind of see is simplifying the API, adding some documentation, making sure it's stable, and then maybe helping the community get this into scikit-learn. But other than that, it's really just going to be based off what the community wants. So I'm gonna let the product market fit be dictated by everyone in this room and the issues that get reported on the GitHub. So yeah. Mhm.
Perhaps also paying attention that this support the streaming natively?
It does, yeah. So there is a streaming implementation. That's a subsequent paper that was introduced in 2016. And so there's a couple of caveats with it. So you do still fit on some data, and then as new data comes in, you actually benchmark that against the original data that you fit or that original distribution.
Yeah.
So if I would say if you can assume that your distribution is going to remain constant as new data is coming in, then you don't really need to refit very often.
Like the context from which
Yeah.
the streaming paper comes from is it was about intrusion detection on older satellites. So for them it was important that they could not do the distance calculation all the time because they had, for all the data points, create the neighborhood metrics because they had old systems that they wanted to retroactively update in order to see if somebody's trying to listen on them and so on. And so they implemented a streaming algorithm which reduces the amount of times that you have to retrain. Like for example, in our case for the observability stuff, it was also useful because we could fit the model, update the model every couple of days, and then just use throughout the rest of the time, just send in the new data points without having to send in a whole bunch of it and have unnecessary traffic.
Yep.
And when you mean trading, you mean sort of within the context of...
Yeah, so if you didn't have the streaming implementation, each time you got a new observation, your matrix would get larger and you'd have to refit on the entire matrix each time. What the streaming implementation allows you to do is skip that, refit on the whole matrix each time piece. Yeah, so it's a lot quicker. It does introduce a little bit more error, but I mean, that's a trade-off. Yeah. Any other questions? Time for lightning talks? Cool. All right. Well, thank you very much for coming. I know it's been a week. I hope you all had a lot of fun, and yeah, thanks again.